Now you should be able to see the screen.
Yep.
Okay. Good. Yeah, awesome. Okay, yeah, let me thank the organizers for giving me the opportunity to present some work here. So this is based on two papers. One appeared last year, end of last year, with this bunch of people, and a paper which appeared earlier this week in collaboration with these two students here in Munich. And let me also start with giving a high-level summary of what I will talk about, in case you want to just know what this is all about. And this is basically about two different questions. The first one being that we want to improve our knowledge of effective field theories by having access to explicit metrics. In particular, this should give us access to non-holomorphic quantities. And in particular, the quantity we are interested in is looking at the metric, and in particular metrics of Calabi-Yau manifolds and SU3 structure manifolds. The other question which we are interested in is we are interested in finding systematics in vacua and flux vacua in particular, which satisfy particular phenomenological requirements and consistency requirements. And this will be about, sampling flux vacua in particular with using reinforcement learning. Okay, let's get started with the first aspect of the story, namely metrics with machine learning. So the metric, as we all know, is key in any extra-dimensional physics model. And this is just, to flag the kind of importance of it. And we all can kind of come up with scenarios where this is where this is important. And over the years, we've seen multiple things, and every one of you has their particular favorite. Just to name a couple of things for people in the audience, one thing where this can have importance is if we're looking at calculating properties of the effective field theory, such as soft terms, in, say, a large volume scenario. This can be of interest if we're interested in D3 brane inflation and understanding the potential. And it can be interesting when we're looking at the massive string spectrum. And this list obviously can be continued. On a more general perspective, this is also interesting because we are trying to understand the effective structures of the effective field theory better, is to see whether there are some structures in these properties that distinguish them from bottom-up BSM models. So if we are thinking about distinguishing stringy solutions from BSM pictures, this is another corner which makes sense to explore. Having said this, and I hope you all agree that we do want to study metrics, the question is obviously which metrics do we want to study? And since the early days, it's pretty much clear that one large class of metrics we would like to understand is that of Calabi-Yau manifolds. And the nice thing is that we know about the existence of Ricci-Flatt Kähler metrics going back to Yau. However, this is coming with no explicit construction. So although we know about the existence of these and we can construct these spaces, we don't know about the explicit forms of those. And obviously, that's what we are after. Now, the simplest examples that we can start with is looking at the complete intersection manifolds in projective spaces. Typical toy example would be, say, looking at the quintic hypersurface in P4, and we want to understand the metric of those. Now, as I've seen on the previous slide, there are other structures, obviously the 3-0 form, which we explicitly know, but what we're obviously interested in is the Kähler form. Now, how can we get this? How can we get the metric? You have to make an ansatz. One ansatz, which it promises to be very fruitful, is to look at generalized Rubini study metrics. So these are metrics which are of this type. Now, if you, these acronyms that I'm putting here in is essentially that we are looking at polynomials in terms of the coordinates. And H being some matrix of appropriate dimension, which encounters the complex structure moduli dependence if we want to study that at different points in complex structure modular space. Now, these are the objects which we want to these H is essentially what we're after when we make this ansatz. Now, we are not obviously the first ones to try to look at metrics, and we're also not the first ones to look at metrics numerically. This has been an effort which has been going on for some time, and there have been various approaches. So let me give a really short overview. There are obviously, people try standard things like finite distance methods. They fail because of the dimensionality of the problem. Now, if you're looking at spectral methods, the situation simplifies, but so this is all the approaches going under the name of Donaldson's algorithm, or often referred to as Donaldson's algorithm. But the problem with those is that they're currently really highly inefficient. So in particular, two things that play a role here is that these algorithms are such that they are evaluating the metric at a single point in moduli space. So if you're interested in something like moduli dependence, this is extremely hard. However, the second point is also important, namely that if you want to go on in accuracy, if you want to get better and better approximation, I mean, this is an approximation scheme of the metrics, this becomes more and more expensive. And I'm showing you here some kind of typical numbers that appear if you know about the algorithms. If to evaluate, say, a T operator, the average time that it needs grows quite quickly. Now, the other question that you can ask is, okay, numerics are interesting, but maybe I'm not interested in just Calabi-Yau metrics. I would be interested in studying other types of metrics. And this is really, a very valuable corner of the string landscape. And we potentially need also methods here to address this numerically. And these methods these spectral methods are not designed for this. So there are no methods to do this. And really, on a practical level, if I'm interested in modular dependence of the metrics, this is not something which is like readily available with these methods. So the question is, can machine learning help in this situation? And first of all, you have to make sure that this is a suitable problem for machine learning. In particular, you have to formulate it as the appropriate optimization problem. This has various conditions that you have to satisfy. Obviously, if you're interested in Calabi-Yau metrics, we're interested in Ricci-flat metrics. Naively, you could formulate this by looking at the vanishing of the Ricci tensor. However, this involves a lot of derivatives. So there's a cheaper alternative to look at these things, which involves less derivatives and hence computationally actually more effective. We are looking at balancing the two top forms that you can construct. And this effectively leads to something which is this often referred to as sigma measure or Monge-Ampere loss. This is what you want to satisfy. The second condition that you want to satisfy is you want to satisfy that you're actually in a Kähler space. If you're starting from a Kähler potential, this condition is trivially satisfied. But if you're just starting from just fitting a metric, this you have to check explicitly. And the third condition is that obviously you're well defined across different coordinate patches. Now, the other thing that you have to satisfy, and this is already known, is how to sample points accordingly. And this is basically standard schemes that have been developed in the context of the, especially from the spectral methods. And this is what we use here. Now, then the question is, okay, can neural networks or particular machine learning help to such problems? And in a wider scheme, this is something which is helping across domains. So we see in a lot of areas that one can address differential equations and solving PDEs with neural networks highly efficiently. And it's a very much ongoing field. And so, for instance, if you're interested in seeing what the state of the art field is, please feel free to have a look at the simulation workshop at SLR 2021. So now this is really, we have formulated this as an optimization problem, and that's basically the properties that our neural network function that we want to output has to satisfy. So in order to kind of optimize these losses, this is something which requires you to be able to calculate the derivatives of these functions as the output. And this is something that you can do with standard auto differentiation. And this can be done in standard packages. We used, we did various experiments in this work. We used various packages, and all have the capability of doing this. Some more efficient than others, but that's basically the story. So now, what I want to report here on is on two different approaches, which have a slightly different scope. So the first one is to learn this H matrix effectively. And then from that, we have a Kähler potential, in which we readily can compute the metric. And the second class of models is where we input a complex structure and a point, and we output the metric. Results I show are for the quintic, and I'm sure we hear also related work from Vishnu later today, where we'll talk also probably about other examples. Okay. So let's see how can we learn H directly. And this is obviously comes with a benefit, namely that the overlap and Kähler conditions are automatically satisfied. So the only loss that we care about in this context is the Moncha pair loss. And now we have to optimize H. Now there are various ways which we can do this. And we did two strategies. The first one is to use data from Donaldson's algorithm to learn H. This is basically formulating this as a regression problem and looking at basically a supervised learning algorithm. This tells you about, that your network is also able to learn H. And in the second approach, we use the sigma measure directly to train H directly. So we don't have to go to Donaldson's algorithm to calculate H. So this is unsupervised. Networks, standard feed-forward dense neural networks, and nothing too fancy. Let me show you a couple of results here. So this is optimizing with Donaldson's algorithm as a supervised problem. And so what we see here is that the network really learns the interpolation between various H matrices. And it even shows good performance outside of the trained area. So for instance, focus on this result down here. This is showing you how well our neural network is doing when we evaluate the sigma measure outside of the range where we've trained it. Yeah, and this is completely, beating, for instance, that you just use the nearest point of Donaldson's algorithm simply to evaluate the metric there. Now, that's good. Let's go a step further and look at optimizing with sigma directly, so no Donaldson's algorithm. So here I'm showing you results where we train a network in the range between 10 and 100. And as comparison, so this is in expansion, this is k equal to 6. So for instance, this corresponds to 42,000 components in H that you have to optimize. And what I'm showing you here are the sigma accuracies that our network achieves in this range. And in comparison, here are the accuracies that you achieve when you run Donaldson's algorithm at the same level of accuracy. Interestingly, obviously, we can test also how well is it performing outside of this area, and you see that it still generalizes well. Obviously, it deteriorates at some point. Now, just as a kind of perspective, it might also be interesting in some applications that you want to go to higher derivatives. We've done this, you can do it, it takes longer, and you might lose a little bit of accuracy, but it's in principle, the technology is there. However, one thing to mention is here that the accuracy is still rather sensitive to the architecture, so we have to do a bit of hyperparameter scanning, and also the range that we trained for. So for instance, I'm showing you here another network which we trained in the range from 0 to 10. And this is doing very well in comparison to k equal to 6. In particular, if you compare the accuracy you have for at psi equal to 0 for k equal to 12 network, we are really getting into that territory with the k equal to 6 answers. Another thing, you play with these structures, with these matrices, and in particular, you can also play with it with Donaldson algorithm. And as an exploratory tool, that's quite interesting because you can also see structures appearing in the components of these matrices. Now, let me mention a couple of other examples. We can also learn G directly. So now we have to ensure additional losses. A key point here is that we use the neural network, as outputs G. But if we do this directly, just output G without any kind of guidance, then the accuracies go, are nowhere good, and we're not getting good results. What is key is that we make some ansatz, which is kind of a perturbation around a known metric, which starts you off in a good, reasonable area. So we're taking here a perturbation of a Fubini study metric. Again, we're using standard feed-forward neural networks, and we use relatively small initialization. Again, it converges. We can play a lot of games. We can play games on, seeing what is the influence of various loss components. And we see that, what is the relative influence of those. And in particular, what we see is that the Monge-Ampere loss is the dominating source in this whole problem. Now, let me flash another very important thing, perspective-wise, is basically now learning this metric network, it also allows us to...
5 minutes.
Okay, 5 minutes. Okay, I need to be quick because otherwise I can't talk about it. So the thing is, here, very quickly, you can modify the loss function. Yeah, so before that, we had dj equal to 0. And now if you're interested in SU3 structure manifolds, you can do this. You modify it. What we've shown here is, yes, especially if you have targets that is this whole procedure works and it converges to the known solutions. Okay, good. So this is, I think, very interesting that we can, get good accuracies with these approaches. We can venture into modular dependence. We can venture into non-Kähler metrics. And that's it. So let me flash a couple of things about this other work, which appeared earlier this week. So let's switch gears. So this is about sampling flux vector with reinforcement learning. And this is another natural question, which machine learning is very much well suited for. And that is to understand the space of string solutions that we have. And now, the question is that, we want to obviously sample the space to understand it, yeah? And this naturally informs us about properties of it. In particular, there are obvious advances in sampling techniques from machine learning. So the question is, can they help here? And can we learn something? So in particular, what I will focus on is correlations between UV parameters for the UV parameters for IR observables. So these correlations enable you to generate particular models. So if you like, for instance, this can reveal something like, okay, you want to look at these type of fluxes to generate a particular type of function. Okay, so why reinforcement learning is a good technique? We've heard from Andrea, a very nice talk earlier this week. And so what we want to do is we want to use reinforcement learning to search for vacuum in a flux template and to find vacuum with particular properties for W0 and G string. And the underlying question here is also a little bit on, what are the best techniques to sample here? And in particular, that's I think, a rather open question of what works best. Our environments are rather simple. So we take exactly the same environments also to provide comparability with the genetic algorithms that were explored in this paper. So this is in particular, these are two moduli examples, pretty much standard. Now, in this context, what we have is a situation with 8 fluxes that we have to turn. In terms of reinforcement learning, we have to walk in this space. What we do is we add and subtract one of these flux quanta. And what we want to tune for is a W0 of order 50,000, same as in this paper, and to be obviously have vacua in the fundamental domain. And we have experiments where we are focusing on particular G-string values. Okay, same story. You have to define your rewards. Here we have played around with a lot of them. And it's good to have somehow, also if you're near to something, near to, say, the fundamental domain, near to the good superpotential value, to give it some incentive to go there. We've trained various algorithms, so various reinforcement learning approaches, and to see also, to explore what is best. And we find quite some sensitivity at the moment to hyperparameters. And I'm showing you here results during training, for instance, what is happening. And what you're seeing is that we are outperforming a Metropolis algorithm, after some time. And there is another technique from deep Q learning, so prioritized experience replay and dueling extensions don't manage to do this. Now let's have a look at more interesting structures in the last remaining minutes, basically looking at, what has the algorithm found. And so when you now see what models it is favoring, so you'll start at some random initial point, this flux vacua, and then this is showing you the time evolution, what it's take, and that's the occupation number, so it kind of gives you the strategies. So, and you see that clearly when you're looking here at the reinforcement results, this is showing you some structures. And on the left, I'm showing you the contrasted results of when you're running with a Metropolis algorithm, and just focusing on successful runs, just filtering those ones out that satisfy the constraint. And you see that there are slightly differences in the strategies. There's still also a couple of structures, but if you were not to filter this out, you wouldn't see anything. So this means
starting into question time.
Okay, just let me flash these things, and then we can go into questions. One is you then can look at the correlations among these, and these structures I don't think people have seen before. Let me skip this. Let me say something about the lessons, next steps. So I think this is interesting. RL can be more efficient, but we should not forget about also cheap alternatives. And the interesting question is obviously, how does it scale with the number of moduli, and compare it also with other generative techniques such as flow models. Good. So let me conclude. Calabi-Yau metrics are very much accessible with machine learning. We can venture into new types of metrics. We have flux vacua are accessible with reinforcement learning, so sampling them is possible. We've shown this here. And this reveals you some hidden structures in the flux space, and there's lots of space for natural extensions. And while I'm waiting for your questions, you can take a look at what the RL agents are actually doing in comparison to Metropolis, how it's actually wandering into the space. So thank you very much for listening.
All right, thank you very much, Sven. Are there questions for Sven out there? Maybe while they're coming in, I'll ask one. I guess I have a few, but maybe I'll just ask one. So one thing that you emphasized here is thinking of RL sort of as a generative model, which is a sort of a new perspective, I think, because we often think of it in terms of doing search, but you're saying that these trajectories are really not just doing search for an endpoint, but they're doing sampling as we sort of follow trajectories towards an endpoint. What are some of the things that your guys' studies in this direction uncovered from a sampling perspective that might have been surprising?
Yeah, so thanks for the question. Yeah, so for instance, what we've seen here is this kind of correlations, for instance, yeah. So these are things where you're saying, okay, how are different flux vectors correlated in this for these properties? This is a structure you can also reveal when you just do metropolis sampling, for instance, but it takes you a lot longer, yeah, to reveal the structure. Yeah.
I see.
And so this is really to get this picture this clear, you have to do a lot more, yeah, let the computer run longer, essentially, yeah, to get it.
I see. So your point is that you might visit a lot of configurations that perhaps aren't good configurations or something like that.
Yeah.
And because RL is upping your statistics, the sampling is happening faster, and therefore you can measure correlations easier. Cool. Yeah. Awesome. That makes sense.
I think that, yeah, there's a lot of interesting things that you can then ask at the end is, are you actually doing a proper probe on the sampling properly?
Yes.
But definitely as a discovery tool for structures, that's yeah.
Well, and I think we shouldn't beat ourselves up if we over questions of doing the sampling properly, because the right sampling, which is according to the cosmological measure on the landscape, is something that no one can come close to doing. Yeah, very good. Are there questions for Sven that have come up in the meantime? Maybe I'll check the chat. I can ask one more. So I know that so the way that you guys are doing these Calabi-Yau metrics is really interesting and potentially generalizable to other cases like G2. Comparing to other corners of the machine learning literature, it's a lot like what neural network wave function people are doing, right? In the sense that there's some function that you want to optimize for some physical purpose. Outside of the context of metrics, have you thought, David Fowl calls these self-generative techniques, right? Have you thought about other potential applications of these sorts of techniques in string theory? Because it's kind of a new thing that you guys brought in, not just with respect to the metric, but also with respect to the technique.
Yes, a little bit. So I mean, the thing is that so what's really nice here is I think that we have a physical constraint, which basically gives us some kind of unsupervised way of like consistency conditions, yeah. So for the on the solution, and that's something that you can explore in differential equations as well as solutions. So there are constraints on the solution space that you can explore beyond just satisfying the equation. Yeah, you can formulate additional consistency conditions, like, for instance, the conservation of certain symmetries of your solution, and that's something that's also relevant for other PDE kind of examples. And yeah, as you probably know, we have played around with this in a different context for simulations of systems to search for these symmetry constraints.
Yes, absolutely.
Yeah.
Yeah, I mean, it's interesting because the technique that you guys introduced is potentially very relevant generally in string theory. Anytime you want to optimize some sort of continuous function for physics purposes, it just happens to be that you're doing it for Ricci flat metrics, but it's much more general, and that's why neural network quantum state people can find ground states. So
yeah, I think the really what is the thing to appreciate is the auto differentiation, respectively.
Yes.
That because that opens you a lot of doors to a lot of problems in some sense.
Absolutely, totally. Anything that requires fast computed derivatives, which is a lot of things. So
and accurately, yeah.
And accurately, absolutely. All right, very good. It seems that no other questions have come in, and we're 1 minute over time. So why don't we transition to the next talk? So thank you very much. Let's thank Sven one more time.